All right, this is problem 9, chapter 9, 123 in the TRO. Assuming that all the energy given off in the reaction goes into heating the house, determine the mass of methane, which is CH4, required to heat the air in the house by 15 degrees Celsius, or 15 Kelvin. Assume that each of the following: the house dimensions are given, gives you the heat capacity of air, and 1 mole of air is 22.4 liters at this temperature. That's what we're going to go with. All right, so first thing, let's do the volume of the house. All right, so the volume of the house, volume is length times width times height. It was 35.0 meters by 25 meters by 2.8 meters in this problem. So if we do that math, that volume looks like it's 2,450 meters cubed. So now we have to take this volume of air and change it into moles. Well, 2,450 meters cubed. Right, and so we're going to convert that. And we know that a meter cubed of air, in this case, is 1,000 liters. And our problem tells us that 22.4 liters is 1 mole. So for air, this gives us 109,375 moles of air. Now we need to heat the air. Right, so how much energy does it take? Well, that's a Q equals MC delta T. It gave us the constant C of 30 joules per Kelvin mole. All right, so Q is equal to, in this case, 109,375 moles of air. Gives us C of 30 joules per Kelvin mole. And delta T from the problem was 15 Kelvin, or 15 degrees Celsius. So Q happens to be 49218,750 joules. Or if you divide that by 1,000, it's 49,219 kilojoules. So that's the heat required. Okay, now, step 3. Let's talk about methane. So methane burning, we got methane is CH4 is a gas plus O2 gas, giving us carbon dioxide and water vapor. Now, we have to use H2O gas here. Use water vapor. All right, so make sure you use the gas. If you use the liquid value here that we're going to get, you're not going to get the right answer. So we go to the back of the book, look up delta HF standard of these. All right, oh, I forgot to balance the equation. Balance the equation. So if I balance the equation, C is good. I need a 2 in front of water. And now I have 4 oxygen, so I need a 2 in front of O2. There we go. So look up delta HFs. For methane, it's negative 74.6 kilojoules per mole. O2 is 0, element standard state. Carbon dioxide is negative 393.5 kilojoules per mole. And water vapor is negative 241.8 kilojoules per mole. For methane burning, all right, delta H of the reaction would be equal to, we have products, the sum of the standard enthalpies of formation of products minus the sum, the standard enthalpy of formation reactants. So, delta H. That gives me CO2 plus 2 H2Os minus CH4. All right, so that gives me delta H now. Plug in my numbers. CO2 is negative 393.5 kilojoules per mole plus 2 times negative 241.8 kilojoules per mole minus negative 74.6 kilojoules per mole. So that gives me delta H of this reaction for methane happening to be 802.5 negative kilojoules per mole. All right, so now finally step 4. The amount of methane. So we have to start with the heat required. And that was back up here, the 49,219 kilojoules. I need, so 49219 kilojoules of heat. And we're going to use some conversions here. So we have negative 802.5 kilojoules is 1 mole of methane. Now I want to point something out. This is negative, which means heat is released. Right? Obviously, we're not going to have a negative amount of grams of methane. So that's just a negative number for heat release. We're not going to use the negative. Then, 1 mole of methane is 16.05 grams of methane. All right. So if I do that, I get 984 grams of CH4. That's a horrible 4. All right, go back up to the top. And I'm not so sure if they're going to count that as 1 sig fig in Pearson, but I'm looking at 2 sig figs right there. So I'm assuming we're going to have 2 sig figs. So if I have 2 sig figs, I'm going to say 980 grams of CH4. So that is this problem. Hopefully that makes sense. Have a good one.